talk about this differentiability and analyticity. For complex valued functions. Let's start with the most basic case. Suppose your f is taking real value, taking real number, and then have complex value, which means that you have this u and v, what we learned from calculus. In this case, the derivative is defined to be, let's say the variable is x. U x derivative plus I times vx derivative. And so if you're taking the derivative at some x naught, then this is how it is defined. So let's say f x equal ux plus I vx. We'll extend differentiation complex linearly. And then for the general case, take a complex number and with complex values. We have to talk about what's called Cauchy-Riemann equations. So this u and v, taking complex numbers and real values. So one would firstly imagine that we just define this derivative to be limit delta z goes to 0. So here z naught is complex number, delta z is complex number that changing approximating to 0, approaching 0, but still legally allow it to be complex number. So there is a problem with that. To be well defined, one has to make sure the limit doesn't depend on how delta z goes to 0. does this mean? So delta z equals to 0 means you are taking complex number and making this complex number has modulus smaller and smaller, right? So in other words, you could write it as real part plus I imaginary part goes to 0. This is equivalent to saying delta x goes to 0 and delta y goes to 0. So this is how just the real part, imaginary part, and so real numbers. In particular, you could imagine that if I choose any two different ways to approach the 0, they should give me the same result. So approach 1, delta z, approach 0 along the real axis, delta y equals 0. Then let's compute what it is. This is so let's first introduce some notations. Let's write this fz to be again u z plus I with z, and for this fz naught, let's denote this by u z naught plus I with z naught. But because we want to say the changing of real part and imaginary part, let's write it as u x naught y naught plus I v x naught y naught. So we are writing z equals x plus I y, and here's z naught x naught plus I y naught. And so in particular, we have this f z naught plus delta z minus f z naught. This could be written as u x naught plus delta x, because we have delta z equals correspondingly, right? So y naught plus delta y plus I v x naught plus delta x y naught plus delta y. This is the first part, minus u x naught y naught plus I times v x naught y naught. Right, so this could be again summarizing to delta u let me don't use the abbreviation, so just put this together, x0 x y naught delta y minus u x naught y naught plus I times x naught y naught minus. Okay, then coming back here, what we have is the first approach is along delta y equals 0, which means that we first let delta y equals 0, then we let delta x tends to 0. Then the numerator will become just copy it here. The good thing is that when you let y delta y turns to 0, then you could simplify this expression a lot. So this would become, so delta y goes to 0 after your first approach. Right, so what do you have is delta x goes to 0. This doesn't matter, you just take limit on both numerator and denominator because they're both non-zero. And so what is left is u0, x0 plus delta x, y0 minus u, x0, y0. The other part is v, x0 plus delta x, y0 minus vx naught, y naught. So you see, what is left is only the limit. Like this is really the derivative. If you just look separately, this part is really the derivative of u with respect to variable x at this x naught, right? So the first part becomes u x naught derivative. Similar reason, second part is v x naught derivative, or write it more rigorously, the partial derivative. So this is partial u partial x at x naught y naught plus I times partial v partial x naught y naught. This is what we finally get. Okay, let's approach 2. We just change the direction, the order. First apply x, delta x goes to 0, second let delta y goes to 0. And then what we got is, obviously, let's just write the result. After the first step, what you got is u x naught and then y naught plus delta y minus u x naught y naught plus I v x naught y naught plus delta y minus vx naught y naught, and then divided by delta y. So this is indeed partial u partial y x naught y naught plus I partial v partial y x naught y naught. And so what can we see now? Sufficient, no, a necessary condition. Not sufficient yet. A necessary condition for f z being derivative, being differentiable at z naught equals x naught plus y naught is that for the two choosing approach, it should already give you the same derivative. That's not sufficient to say that, well, all the different approaches have the same name, but it is necessary that for this choosing to approach, it must coincide, and this already tells you that because they are all real value functions. So you just compare the real part, the imaginary part in some sense, and you have to conclude that partial u, partial x at this point have to equal partial u, partial y. Sorry, let me see. Did I make some mistake? Yeah, I made a mistake. So here, what we have is I delta y, right? So what we really have is 1 over I times this. So this should finally be, this is actually partial v, partial y, x naught y naught, and then 1 over I, 1 over I. It's minus I. Partial u, partial y, x naught y naught. And so finally, partial u, partial x should corresponds to partial v, partial y. And partial v, partial x equals minus partial u, partial y. So to summarize this, just to briefly write partial u, partial x equals partial v, partial y, and partial v, partial x equals minus partial u, partial y. This is a necessary condition that the real part and the imaginary part of your f have to satisfy such that it will be differentiable at a complex number z naught equals x naught plus I y naught. So which means these have to hold for that point. So let's abstract this condition. So this is called Cauchy-Riemann equation. we see that f is differentiable at Z0 if the derivative defined by the limit just described above is well defined. At this point Z0. Remark. For differentiable function f equals u plus iv, we have seen, or we have shown, that f is derivative at z, because if it exists you can choose whatever approach. Using approach 1, this is partial u partial x. That tells you how you can compute the derivative, right? You just compute as how you compute the derivative of real functions, and then you use this formula. But also use approach 2. This also equals partial v partial y minus I partial u partial x. Partial u partial y, yeah, both on y. And so this is again a necessary condition. But what is amazing that it can be shown. What is magic? It can be shown that so the Cauchy-Riemann equation is also sufficient. And as a conclusion, finally, our conclusion is that f is differentiable at z if f is well defined as z0, if and only if and only if f satisfies Cauchy-Riemann equation at point z0. And we will see that f is analytic in neighborhood u of some complex numbers not if it is differentiable. Everywhere in U, we see that it is entire if it is analytic on the whole complex plane. Sometimes analytic is also called regular or holomorphic. So we are discussing the exercise part. Example, f equals z is entire, and f equals the conjugate is not differentiable. Not differentiable anywhere. Not even see it's not differentiable at some point, it's not differentiable anywhere.